PowerPoint. Right. Share screen. Let's see. Where's my share screen? Share. There we go. Screen. Share. Okay, I think we're ready. Show from beginning. All right. I think we're ready to go. There are about a bazillion different pieces to the lecture this week, so I apologize in advance for that. So we're talking this week about reliability and reliability in a latent variable framework, and then also we're going to talk a little bit more about equivalence and nesting. So we'll start with reliability, and then we'll move to equivalence and nesting. And the homework has sort of two shorter problems, one on reliability and one on nesting and equivalence. All right. All right, so you're all probably familiar with at least a little bit familiar with reliability, I'm assuming, right? Chromebox Alpha, everybody's heard of Chromebox Alpha, yeah? Okay. So I don't know if you remember what you were told in your intro measurement classes about the assumptions that Chromebox Alpha makes. Does anybody remember anything? We always say Chromebox Alpha assumes tau equivalence. Does that ring a bell at all? No? Maybe? Sure, okay. But then the next question is, even if that sounds familiar, what the heck is tau equivalence, right? Because that you might be a little less, I mean, I feel like that's something we always say, like Chromebox Alpha assumes tau equivalence, but we're going to kind of unpack what the heck is this thing called tau equivalence, and you know, what does that mean if we don't meet tau equivalence? And actually, you know, Chromebox Alpha won't be a good estimate of your reliability if you fail to meet tau equivalence. And so, the larger the violation of tau equivalence, the more Chromebox Alpha could actually underestimate score reliability. Although I want to sort of give a caveat there and say that there are a lot of different ways that you could sort of violate the assumptions of the model. So we're going to talk about tau equivalence as one particular thing, but there's another potential violation that could actually inflate alpha, and that's if you have correlated errors. So we're not really going to estimate a model with correlated errors today, but we can sort of think about that. So if you think about, imagine you have, well, does everybody remember sort of how Chromebox Alpha works? What are the fundamentals? Now, what's it a function of? You don't have to remember the formula, but what is Chromebox Alpha a function of? Or coefficient alpha? What's the difference between Chromebox Alpha and coefficient alpha? What do you know? So Chromebox Alpha uses the unstandardized variance covariance matrix, actually. So it's like an unstandardized, it's using unstandardized stuff. Coefficient alpha actually is the same computation, but using the correlation matrix instead of the variance covariance matrix. And like most of the time, the estimates that you get from Chromebox Alpha and coefficient alpha are super close. Because again, it's sort of the difference between, you know, it is the difference between using a variance covariance matrix and using a correlation matrix to make your computation. So 99% of the time, they're within, you know, a couple thousandths of each other, so it doesn't really matter. Occasionally, they will diverge, you know, because of wonkiness or whatever. And, you know, in that case, you have to think a little bit harder about which one you're going to report. But the vast majority of the time, it doesn't matter too much whether you use sort of the Chromebox Alpha or the coefficient alpha. Okay. Coefficient alpha, though, is easier to think about because it's always easier to think in correlations than it is to think in variances and covariances. So even though we're going to do everything with Chromebox Alpha, let's just sort of start by thinking about coefficient alpha. What is coefficient alpha a function of? Well, it's really two things that drive coefficient alpha. The average the average the average inner item correlation and the number of items. And coefficient alpha is it's just a function of the average inner item correlations and the number of items. And alpha increases as the number of items increase, and it also increases as the average inner item correlation increases. Okay, so think about the average inner item correlations, right? Imagine you have a correlation matrix and you have a whole bunch of correlations in that correlation matrix, right? Imagine that two items are really correlated with, imagine you've got like a single fact, it's unidimensional. We also assume, should have started with that. Chromebox alpha also assumes unidimensionality, right? So we're assuming we've got one factor. But now imagine you've got sort of a single factor, and imagine that, let's say there are correlations of possible, but for now, I'm just going to put it down. So what would the average inner item correlation here be? 0.6 something, right? So if you were fitting a single, imagine fitting sort of a single factor model to something like this, right? What do you think might happen between items 1 and 3? That's where that 0.9 is. I mean, again, this is a bad example because actually single factor model will fit perfectly when we only have 3 items. So I should have a 4th item there. But what I'm asking you to think about is, imagine there are 2 items in a unidimensional space and they correlate with each other way more than they correlate with any of the other items on the scale. So you get something like that large 0.9 correlation between 2 items, and then all the other correlations, let's just say, among the other items are moderate. So 2 things are going to happen, right? Like that's going to increase the average inner item correlation. What's that going to do to alpha? It's going to increase alpha, right? So your alpha is going to be higher than it should be, right? How would we model that in SEM? If we thought we have 2 items that are more closely related to each other than would be explained by the overall factor, we'd correlate the errors. That's exactly right. So that's why I'm saying, if you have a factor structure where there are correlated errors, that is actually going to push Chromebox alpha up, right? It's also, in some sense, if you think about it, it is unmodeled multidimensionality, right? There's something that those 2 items have in common. There's some factor out there, right? Maybe it's a wording thing. Maybe it's, it could be lots of different things, but these 2 items have something in common that is not explained by the factor that we're modeling. There's probably some other factor out there, some other latent variable out there that would actually explain why they still have something in common even after controlling for the factor, right? Okay. So I feel like, if you sort of hang on to this idea that coefficient alpha that we assume tau equivalence and that Chromebox alpha is an underestimate if we fail to meet tau equivalence. I mean, which is true if you don't have any correlated errors whatsoever. It's easy to sort of lull yourself into a sense of complacency and think like, oh, well, whatever Chromebox alpha is, it's, if I don't mean tau equivalence, it's just going to be an underestimate. So if it looks good, I'm fine, right? Which is not actually the case, because I would say correlated errors are at least as big a problem as this issue of tau equivalence, and that can push your alpha estimates down. So what that means is, if you're not meeting the assumptions for Chromebox alpha, and you don't know how you're not meeting the assumptions for Chromebox alpha, you really don't know if Chromebox alpha is an underestimate or an overestimate. But you do know that it's not right? There are better ways to compute reliability. So there's been actually a lot of sort of hubbub in the measurement and methodological world over the last 4 or 5 years, probably, about sort of the misuses of Chromebox alpha and how Chromebox alpha is not the be all and end all, and that we should be using other measures of reliability. Does anybody know any of the other measures that are sort of being touted as better measures of reliability than Chromebox alpha? Coefficient omega. This is the heyday of coefficient omega. It sounds fancy, right? Omega, it sounds good. So what I'm going to show you today, actually, when we go through this latent variable modeling approach to reliability, we're going to actually estimate coefficient omega. I don't always call it that. I just call it the reliability that falls out of the congeneric model, but I think I should start calling it omega because omega is popular, and that's what it is. All right. So let's talk about how we're going to estimate reliability using structural equation modeling or latent variable models, right? So we're sort of back into measurement models, and we're thinking about reliability. And remember that reliability conceptually is just, and we have talked about reliability conceptually throughout the semester, right? It's just the proportion of true score variance to observed score variance. So it's you've got the sort of total variance in some, your total variance, right? And what proportion of that total variance can actually be attributed to the true score, which is also the latent factor. So here we're going to use T to mean the true score, which is really the variance that's attributable to the latent variable. And here we're going to use X, although I may sometimes slip and call it Y. I'll apologize in advance if I do that. But X we're going to call the composite observed variable. So that's really, again, when we think about reliability, we usually want to think about reliabilities of multi-item scales, right? Okay, so now we have to talk about sort of a series of we always have these increasingly constrained models in this class. So now we have a series of increasingly constrained measurement models. Now, again, the last couple of weeks, we've been talking about multiple groups models, and we've been making constraints across groups. That's not what we're doing here. We're going back to a single group. So, and again, any of this could be extended to multiple groups models, but we're not thinking about multiple groups. We're not constraining anything across groups. We're making equality constraints within a group, within a given model. Okay, so a congeneric model, fancy term, a congeneric model is just a unidimensional model. So where we have factor loadings, we have error variances. There are no constraints on the factor model other than those that are required to identify the model. So if you fit a single factor model, just a regular garden variety single factor model, that is a congeneric model. That's just the name for it. So nothing special. We've done a bazillion congeneric models. They're just, regular old models. Okay. The next model is what's called a tau equivalent model. And again, this is what's assumed when you use Chromebox alpha. A tau equivalent model, again, these are going to be increasingly constrained models. So we go from sort of congeneric to tau equivalent, and tau equivalent has any constraints that congeneric has, plus equal factor loadings. So in a tau equivalent model, we actually constrain all of the factor loadings across all of the items to be equal. And again, remember, we're always starting off with this assumption of unidimensionality. So we're going to do this within a factor. So if you had multiple factors, you wouldn't actually constrain the factor loadings to be equal across all the factors. You're going to constrain the factor loadings to be equal within a given factor, right? And we're always just going to be looking at this one factor at a time today. But so we have equal factor loadings, but we don't constrain the error variances to be equal across the items. So that's a tau equivalent model. So loadings are the same. And what does that really mean when we say that the loadings are the same? Really saying that the factor is equally predictive, right? Like again, the loading is really like a regression weight or a slope, and it's really talking about how well the factor can predict responses to that item, right? And remember that if we square the standardized loading, if we take the standardized loading and we square it, that gives us the proportion of variance in the item that's explained by the factor, right? So what we're going to do is we're going to constrain the factor loadings to be equal, but we don't necessarily have to constrain the error variances to be equal. And a parallel model has all of the constraints of the tau equivalent model, so equal factor loadings, but we're also going to constrain the error variances to be equal. Yeah. This is separate from the multiple groups. It's a whole set of constrained models, but not multiple. It means they're all constrained to be equal. So I'm going to, yeah. So we can, I actually, in the code, I'm going to show you, we're going to fix the variance of the factor to be 1, and then we're going to constrain the loadings to be equal to each other. Yeah. So in the code that I'm going to show you, it works a lot better if you fix for the tricks that I'm going to show you. Fixing the factor variance is definitely the way you want to go. But you are right, actually, that if we were to want to fix all of the loadings to be equal to each other, all the unstandardized loadings, one way to accomplish that would just be to fix all of the loadings at 1. Again, that's not exactly the strategy we're going to use, but that is exactly, theoretically, the other way we could do it. Yeah, right. Yeah, and again, and especially when you see the next step of what we're going to do to kind of get what we want. Yeah. Because we're going to use phantom variables again today. It's very exciting. I love my phantom variables. So, yeah. So anyway, but so in a parallel model, then we have equal loadings and we have equal error variances, right? So you think about it, if you're saying like the loading is equal and the residual variance is equal, right? That's actually a very strict assumption. So now you're really saying that the total variances would need to be equal to be able to get something where the factor loadings are equal and the error variances are equal. Yeah. The error to be close to 0? No, we might hope, but remember, because again, remember that the standardized loading squared is the proportion of variance that's explained by the factor. What's a normally pretty good standardized factor loading? You're in instrument design, right? What would you be happy with? Ooh, I go, you can go a little higher than that. I'm never happy with 0.4. And you know why I'm never happy with 0.4? Because I square that in my head and I say 0.4, that means that only 16% of the variance in this item is explained by the factor, which means 84% of the variance in the item is not explained by the factor. It's explained by other stuff. And when I think about it that way, I'm like, that doesn't sound very good at all. Right? And 0.5, which is often sort of a threshold that some people use. I mean, a lot of people use 0.4, so I don't mean to beat up on you because 0.4 is like in all the books. I'm just saying I don't like 0.4 because 84% of the variance unexplained just seems not that good to me. Even 0.5, that leaves 75% of the variance in the item unexplained by the factor, right? And if you get up to, your factor loading is 0.71, that means half of the variance in the item is explained by the factor, and half of the variance in the item is not explained by the factor. So 0.71 sounds awesome, right? You get factor loadings of 0.71 on all of your items, you'd be like, this is awesome. But when you think about it, I mean, it is good, but it still means that half of the variance in every item is not explained by the factor. So to go back to your question of would we think the errors would be near zero? Like, I wish, but in reality, we're actually pretty happy if we're explaining, we're actually very happy if we're explaining half of the variance in an item. And often we're doing a lot less well than that, right? Okay, so, but again, a parallel, when you constrain the factor loadings to be equal and the error variances to be equal, then you're really saying that these items have the same variance, right? So they're not just equally, like the loadings are saying, oh, the factor sort of equally predicts all of these items. That's good, right? I mean, if you think about it, we'd like our items to sort of be equally predicted by the factor. And then, you know, but then constraining the error variances to be equal is really saying each of these items has the same amount of variability. Which, again, if you stop and think about it, that's a pretty, that's cool, but it's also pretty, that's a pretty stringent, it's a pretty stringent test. So again, this is one of those cases where, you know, it really becomes, you know, it's nice to be able to have a set of parallel items. Often people in the test construction business are looking for sets of parallel items, but like, you know, regular old researchers developing their own measures are not usually that worried about having parallel items, but having tau equivalent set of items is really nice. So again, imagine this, equal factor loadings. So the relationship between the factor and the item is sort of equal across all the items, right? The factor equally predicts scores on each of the items. What do you often do with a set of items? When you have a subscale, right? You've got an instrument, you've got a scale, a unidimensional scale. What do most people who haven't taken this class and seen the light and do everything in a latent variable modeling framework from then on, but you know, mere mortals, what do mere mortals do when they have a scale? Before they, you know, they've given a scale to a bunch of people and now they're gonna use that in their analyses. What do you do? Yeah, you either take the sum of all the items or you take the average of all the items. By the way, any preferences? Does it matter? Should you take the sum or the average? What? Well, if they're reverse scored items, you have to reverse score them, right? It's like whatever you do before you create a scale, you've got to reverse score the items or you're going to have garbage. But okay, so putting aside reverse scoring the items, should you take the average or should you take the sum? You say take the sum? Anybody want to say take the average? Take the average? Okay, why? Anybody have a rationale? I think I heard the right thing. What'd you say? Yeah, I mean, I think the big advantage of taking an average rather than a sum is you can always take the average, even if like, imagine you've got 10 items. If somebody skips an item, you can take the average on the 9 remaining items. But if you take the sum, their score is going to be artificially lower just because they skipped an item, you know, which is problematic, right? So I would argue that taking the average, I mean, although, again, theoretically, if you have no missing data, it doesn't matter. But if you have missing data, you know, that's sort of one way to deal with minor amounts of missingness is you can still take the average. But if you sum, you're either not get, I mean, actually, in a lot of programs, if you take the sum, you're just going to get missing for the sum score. But if you don't get missing for the sum score, if it puts it in as a 0, I would argue that's like even worse, right? Now that person is basically going to be a low score on whatever you're measuring just because they skipped an item or 2. Okay, but whether we take the sum or the average, let's say we're taking the average, what does that mean? What is our implicit model of how the factor relates to those items? if we're going to take a sum or an average? Yeah, we're saying that each of these items is sort of equally related to the factor, equally predicted by the factor, that each of these items is an equally good measure of the factor, right? And so if you're creating a scale score by either averaging or taking the sum, either one, then you are actually implicitly making the assumption of a tau equivalent model. You're really saying, I think each of these items is equally predicted by the factor, that they're all equally good indicators. Now, but anybody who's run a factor analysis and looked at the results has probably seen some items have higher factor loadings than others, right? So not all items are equally good predictor or equally well predicted by the factor, right? An item with a loading of let's say you've got an item with a loading of 0.4 and an item with a loading of 0.8. I mean, obviously, the item with the loading of 0.8 is much more strongly related to the factor than the item with the loading of 0.4. But when you take the average of all of those items and just sort of smush them together, then you're giving as much weight to this item that's, what did I say, 84% error. You've right, as you are to an item that's 36% error, right? So another reason that we really kind of need to think about these things and look at these things and, whatever. Okay, enough said about that. So again, we're starting out, for everything we talk about today, we're going to assume a unidimensional factor with no measurement errors. There are computations of reliability that take measurement error into account. They're not that hard. It's just, you can only do so much in a given day. So, okay. So how are we going to do this? Here's our phantom variable. All right. So here's what we're going to do. Actually, ignore the extra 1 for the marker. There's like a marker variable 1 there. There are like 5 ones instead of 4. Ignore the 1 marker variable 1 because we're actually going to fix the factor variance to be 1. But otherwise, this is a good picture. So imagine that we have a 4-item scale that we're going to be using, and we're going to look, it's unidimensional. And so I'm going to call our factor here T for the true score. So T predicts X1, X2, X3, and X4. And obviously, all of those X's are also measured with error, right? So we've got E1, E2, E3, E4. Those are our errors. And then we want to estimate the reliability. Actually, I'll show you a couple different ways you can do it. But one of the easiest ways that you can do it is to basically create a phantom variable that's going to serve as our composite. It's basically going to kind of serve as our composite score. So the phantom variable is X. And notice that the paths from X1, X2, X3, and X4 to X are all fixed to be 1. Which again is sort of like what you do when you create a total score or mean score, right? You're actually weighting each of those items equally, right? So we're going to sort of fix those paths to be 1. X is going to be a phantom variable. Again, it's not even really a latent variable. It's just sort of this phantom variable that we're going to use as sort of a trick. And then we can actually, and basically this phantom variable is going to kind of serve as the proxy, let's say, for the composite observed sort of score. Yeah. Well, X is a phantom variable. It's not a regular old latent variable. And yeah, we do. So here's the thing. This whole entire semester, we've talked about what are called, like reflective models, where we've always assumed that the latent variable is causing the responses to the observed variables. But there are actually, if you go into sociology, I'm not going to malign this, but in sociology especially, They actually do a lot with with sort of what they call formative or causal sort of indicator models, where you don't actually think that there is this latent unobserved variable out there that's sort of responsible for your responses on this item, but rather I want to create this composite variable out of different scores. And a perfect example of this is actually SES. Like SES is not really, I mean, again, often the way that it's sort of conceptualized in sociology, especially, it's not really a latent variable. It is a function of income, education, and occupational prestige. And those things are, I guess it depends on who you talk to. They're like, let's say if they're unweighted, they're all going to sort of have a weight of 1. Then if they were weighted, you could theoretically create some sort of a weighted SES score, right? You could weight income more if you wanted or something like that. But that, that idea of sort of taking items and sort of making them into a composite variable, if you think about it, that is a sort of a reversing of the arrows, right? It's like the items cause whatever this thing is. So actually in latent variable modeling, there are these 2 different kinds of latent variables, but this kind is not the same. It's like, it's not, you don't get the same kind of partitioning of the variance into the variance that's explained by the item and the variance that's explained by the true score. It's more of a, I mean, this is probably not fair of me, but it's sort of more of a tool to get these composite variables. And so you were very astute to notice that the arrows are absolutely reversed here. But again, if you think about, if we were to just take 4 items on a scale and we were to add them together or average them to create some sort of a composite variable, again, conceptually, our arrows are kind of reversed. We're saying, I got these items, I'm going to use them to create a score. Again, notice, no more ease, no more way to partition out the true score variance from the error variance. So there are definite downsides to that approach, right? But yeah, okay. So X is our phantom variable, and it's going to be basically a stand-in for the composite score. That's exactly what it's sort of standing in for. So we're saying X1, X2, X3, X4 are all equally weighted. We're giving them all weights of 1, and they all predict this sort of, X is going to be your scale score, basically. It's like this proxy for your scale score. Okay. Now, here's a question. You could like dig back into your measurement roots. So we said reliability is the proportion of true score variance, right, to total variance. But like, what is the relationship between the true score and the observed scale score? Anybody know? Well, it turns out that the relationship between the true score, I mean, if you think about it again, if we're saying that the total variance the relationship between the true score or scale score is actually so, and again, if you sort of about, how regression coefficients and proportion of variance work, right? It kind of makes sense. The correlation between the true score And the scale score is the square root of the reliability. If we square correlation between and the observed score, get the reliability. Yeah, it's sort of like if you have a correlation between X and Y, right? So let's say Y are correlated. Here's the R, right? If I take R squared of Y, that's explained by X. Another way of correlation, I can also say it's the proportion, right? But here, R is the relationship between X and Y. R squared is the proportion of Y. That's explained by X. The proportion of the total variance and the true score variance, that's reliability. Reliability is in correlation between the true score and the observed score is just the square root of the reliability. That tells you how strongly correlated are the true score and the observed score. All right, why do I care about that? Well, it becomes important in going back to our model with our phantom variable. So I've got this funky latent variable with causal indicators. It's a phantom variable. That's X. And I've got T, my regular old unidimensional, plain old latent variable. And I can look at what is the model implied correlation between X and T. What is the model implied correlation between that X variable and the T variable? And that's going to fall out of our output. I'll show you where on the output it is, but if you just look at, just look at the model implied correlations, and there it is. So let's say the model implied correlation between X and T is 0.9. Well, that is correlation between and the scale score. So all I have to do is take that model implied correlation, square it, I squared equals 0.81, and that will be the reliability estimate for the model. So one way to estimate reliability, again, this assumes like no correlated errors, right? It's just, but one way to estimate the reliability here is just to fit a model that looks like this. Look at the model implied correlation between the true score, which is that latent variable, and our sort of weird phantom variable proxy for the composite score. Take that correlation, square it, and that will be the proportion of true score variance to observed variance, which will be the estimate of reliability in our model. I'll also show you the computation. If you want to compute it longhand, I'll show you the computation for that as well, and I'll show you that you get the exact same thing, whichever way you compute it. So, all right, questions about any of this? Does it make sense so far? You good? All right. I probably got ahead of myself here. Yeah, I did. So this is what I was saying. The reliability is the proportion of variance in X that's explained by T. It's the square of the correlation between X and T. Okay, so how are we going to do this in M+? All right, here's what we're going to do. Again, it's going to work out best if we want to use the trick that I was just talking about to freely estimate all 4 loadings. And so we're going to say like factor 1 by, or whatever you want to name your factor, by x1 star, and notice that the star there, that is what causes it to be freely estimated. And so by default, M+ always assumes that you want to use a marker variable strategy, which is equivalent to writing x1 at 1. Like we don't have to write x1 at 1, but what M+ is understanding when we write factor 1 by x1 to x4 is, oh, you really mean x1 at 1, and then you're going to freely estimate the loadings for x2, x3, x4, okay? As soon as I tell M+, no. Star always, by the way, I don't know if you've seen stars before, but when you put a star in the code, it always means to freely estimate that, whatever it is. And you can actually put a number after that if you want. And if you put a number after a star, that's actually how you get a start value. So if you, this is kind of a good thing to know, because if you ever hit a really wonky, difficult problem and things don't converge, sometimes M+ will spit out, it'll give you where it stopped. It'll give you all of the, it hasn't converged yet, but it gives you all of the parameter estimates sort of where it was. And actually it spits them out in basically this input format. So it'll say like, x1 star 0.432, x2 star 0.475, or whatever. And then you can actually basically copy and paste that from your output and bring that into your input file. And every place that it has star with a number, it will use those numbers as starting values to get the thing running. And sometimes that can be helpful. Again, more often than not, you have a more serious problem than will be solved by this, but occasionally it does help. So star just means freely estimate. If you put star, you could put star 1 here, and that would mean freely estimate with a starting value of 1. You don't need to do that. I'm just kind of explaining the code. Okay. So we don't have to put star for everything though, because as soon as you tell it you don't want the first one to be fixed at 1, it assumes that you're going to freely estimate all of the loading. So we just put it on the first one. And then, because I'm doing that, obviously I'm going to fix the factor variance to 1. So I said factor 1 at 1, which fixes my factor variance, right? And now x is going to be my phantom variable. So here I say x by semicolon. And basically that's saying like, okay, I have a latent variable x, because x by means it's, right? That's sort of called a latent variable. This is a latent variable measured by, but it's measured by nothing because it's not your traditional latent variable. It isn't actually predicting anything, right? X by it's measured by, we got a latent variable, we've got indicators, we've got paths going from the latent variable to the indicators, but that's not what we have here. So I say x by semicolon. So that just basically sets up my x, but it says, okay, there are no indicators. And then I say x at 0. My x is about to become an endogenous variable. In my next set of codes, I'm going to have all of these x1, x2, x3, x4 predicting x. So it's endogenous. But I don't want a disturbance variance on this thing. I just want, again, it's sort of this way of creating this composite variable for me. So I'm going to say that this disturbance variance of x is 0. So it's those two codes that are going to kind of set up this phantom variable for me. X by semicolon, and the disturbance variance of x is 0, x at 0, semicolon. Great. Now the next 4 lines, I basically say, okay, x is regressed on x1 at 1. X is regressed on x2 at 1. X is regressed on x3 at 1. X is regressed on x4 at 1. So I'm just saying x1 to x4, my 4 indicators predict x. And those 4 paths are constrained to be 1, which means they're constrained to be equal, right? And then in terms of output, you don't really need tech 1 and tech. There we go. So tech 4 is going to give you the latent variable variance covariance matrix. So you don't really need tech 1 and tech 3 in this case. C interval is useful to have because you might want to have confidence intervals around your reliability coefficient. And if you want to bootstrap those confidence intervals, you could do that. And I'm just using regular confidence intervals here, but bootstrap ones might be nice. So for sure, you're going to want C interval and you're going to want tech 4. Probably want your sample statistics too. And that's it. And fitting this model is, and again, we're going to do this one factor at a time. So if you had multiple factors, let's say you've got a 5-factor model, you're going to fit each of these just one factor at a time to get your estimate of the reliability. I mean, I would recommend one factor at a time. Yes. That's a good question. You know, it's an at, it's not a constraint. So if you went x1, I mean, I have to check. If you went x1, x2, x3, x4 at 1, I'm not sure if it would constrain all 4 or if it would just constrain the x4 to be 1. What I mean? But again, there are people who are much smarter at coding than I, so there may be a shortcut that I'm not aware of, but I do it like that because I really need each of those to be constrained to be at 1. So, you know, if you can find a shortcut that constrains them all to be 1, that's great. But it's a little bit different from when we do the, you know, when we name constraints and we can sort of say 1, 2, 3, 4, right? All right. Okay. So all we do is we estimate the model. We square the model implied correlation between the true score and x. That gives us the proportion of true score to observed score variance, and that is the reliability. So we can also use model constraints to compute the reliability, and this is going to give you the same thing, actually. So it's your choice which one you want to do, or both. I mean, I kind of like doing both because I can see they're the same, but you don't really need to. So here in the model constraint command, I don't know that we've done this before, but you can actually, in model constraints, I mean, we've done some constraints, but I don't think we've created a new variable in model constraints. So notice the first thing that I'm doing is I'm creating a new sort of, not really a variable. I shouldn't call it a variable. A new parameter, really what it is. It's not a variable, it's a parameter. So I'm creating a new parameter, and it's called reliability, rel, for reliability. And I can actually compute the true score variance. So the true score variance is actually actually the sum of the squared factor loading. That is the true score variance. So you can see here that if you remember from the last slide, the factor loadings were, I gave names to. Did I give names to them in the last slide? I didn't. I should have. Okay. I do in our model when we do it. So what I would need to do is up here, I'm going to give these factor loadings the names B1, B2, B3, B4, just the way we do in parentheses, right? So here I could actually say B1 to B4 in parentheses. I think I have a slide that does that after this slide. So that was really silly of me. Let me see. That one's got at 1. Okay, I take that back. Okay, but anyway, back here. There we go. Slide 16, do I have it? Okay, because I definitely have it in our M+ code too. So in slide, yeah, I have it. I just have 1 there because it's B1. But anyway, so I can name my factor loadings, right? I can name those parameters B1 to B4, and I can name my error variances T1 to T4. And then I can actually compute the reliability. It's just a function of the sum of the squared factor loadings. That is the true score variance. And the sum of the squared factor loadings plus the sum of the error variances, that is the total variance. Like if you think about it, the total variance is the explained variance plus the unexplained variance. The explained variance is really just the factor loadings, right? The sum of the factor loadings is the explained variance, and the sum of the error variance is the unexplained variance. So you can easily set up some code in M+. If you can estimate a new parameter as a function of some old parameters, you can, first thing you have to do in M+ is you have to name the parameter. It'll give it if you don't give it a name. So first you're going to say new, give it a name, and then always the named parameter needs to occur on the left side of the equal sign. They'll be like reliability, equals, and then you can have a formula on the right side that explains exactly how you want to compute that parameter. Yeah. Oh, sorry. Double star 2. There are 2 ways to say you want to square something in M+. You can either do double star, or you can do the little carrot hat thing. either of those will square something. And I think I vacillate back and forth on the code. Sometimes I use star star, and sometimes I use the little caret top in our code. But either of those is square. If you want to do square root, by the way, and there are codes, I think ln is the, you can look in the M plus manual, but like ln and gives you the natural log, and there are all different kinds of functions that you can use in M plus too. So so sometimes this comes in really handy actually to be able to compute something. Again, especially if you're doing something a lot, it's kind of handy to just like have the computations sort of fall out of M plus, and then you don't have to like compute stuff by hand when you're done. All right. That makes sense? All right. So again, we're really saying that each item measures the same sort of, measures the same latent variable. Could have, those items could be on different scales. They could have different degrees of precision. They could have different amounts of error. And the loadings are allowed to vary across items. And then you can see down here, this reliability, the reliability coefficient that we just computed is coefficient omega. So that's what it is. So it's a reliability coefficient, but it's not assuming that we have tau equivalence. It's taking into, right? It's just, you can see that, there was no assumption there. Okay. So next. All right. So look at all this. How do I have that again? I don't know. Okay. So the tau equivalent model. So the tau equivalent model is going to be the same as the parallel model. I thought it's silly because we haven't talked about the parallel model yet either, except for the item error variances are going to be free to vary. So again, what we're really saying is that the items measure the same latent variable. They should be on the same scale now, with sort of the same precision, but with possibly different amounts of error. That's our tau equivalent model. Okay, so for our tau equivalent model, what's going to be important here is that we now actually constrain all of these loadings to be equal. And again, I think the way that I'm going to suggest that we do it, there are a couple of different ways that you can do this, but the way that I'm going to suggest that we do it is actually to constrain constrain the factor to be equal to 1, the variance of the factor to be equal to 1, and then to constrain all of the loadings to be equal to each other, rather than in this picture actually showing all of the loadings constrained to be equal to 1. And that is one way you can do it, but I find things fall out more nicely if you do it the other way. So for example, this is showing you could do it with factor loadings equal to 1, but I'm going to suggest that rather than using this specification, use what I'm calling the alternative specification, which I think actually is nicer. So let's look at this one. So here we've got, and again, especially if you want to compute the reliability using the model constraints that I was talking about, or not model constraints, but the constraints that I was talking about. So here, what we're going to do is say factor 1 by, I see I switched to y's for some reason, by y star, and then I'm naming that B1, and then here I've got y2 to y4. Now, notice here, because I don't have a semicolon, that's actually a continuation of the first line. So if I had a semicolon there, that would be saying the variances of y2 to y4. But actually, because there's no semicolon, it's saying factor 1 by y1 star b1, y2 to y4 plus. Do you see that? Like I should have put that all in one line so as not to confuse you. But just remember that M plus thinks it's all one line unless you have a semicolon. That's why if you miss a semicolon, you mess M plus up so much, because it just keeps reading that line as if it's, you know, and then it'll be like, there's no variable named whatever, you know. So here I'm just constraining all the factor loadings to be B1. I'm not constraining the error variances to be equal, but I am naming them T1 to T4. So that's what that line is saying. Y1 to Y4. I've got 4 error variances. I'm naming them T1 to T4, but they're not constrained to be equal. Factor 1 at 1, right? So we're the factor variance of 1 is 1. And then we're going to say, we're going to create our phantom variable. So you can see I have the x by semicolon, and then down at the bottom, I have the x at 0 semicolon. And then again, I have x regressed on y1, y2, y3, and y4. And those are all constrained to be halves of 1 for my output. Yes. No, I mean, it matters that you have it in the right command. So you got to have model stuff in the model command, but it absolutely doesn't matter what order you put things in. So yeah. Well, oh, yeah, I mean, almost. I guess what I would say is I would start with the Congeneric model and fit it because it's your baseline model, and it's going to be the best fit that you're going to get as across these measurement models. So I would recommend start with the Congeneric model, get the model fit, get the coefficient omega, then fit the tau equivalent model, and then you can do a chi-square difference test and look how much does assuming tau equivalence worsen the fit of the model. Because I think that is really more what again, I think that's the key thing. It could be, for example, in what you were suggesting is you could fit that model and the fit could be horrible. That doesn't necessarily mean that the Congeneric model is going to fit any better. There could be other reasons for the horrible fit, right? So I think for that reason, it's good to start with the Congeneric model because, if the Congeneric model doesn't fit, then tau equivalent and parallel are only going to be worse, right? So you've got other model problems, which would suggest maybe, what does it suggest? I won't say. You say. What does that suggest? If the Congeneric model doesn't fit well, what does that mean? Remember, we got a single factor model, unidimensionality. Yeah. If the Congeneric model doesn't hold, you've got a problem making the assumption of unidimensionality, right? And that's, again, why I would start there and find out because that's another assumption you're making. Congeneric model assumes unidimensionality. It assumes no correlated errors, but it doesn't assume tau equivalence, right? But you could be wrong there too. Yes, Katie. Yeah, so Y1 to Y4, because they're just hanging out there, right? And they're endogenous, the Y1 to Y4 endogenous variables. So that's really talking about the residuals for Y1 to Y4. So those are our measurement errors for Y1 to Y4. And then putting T1 to T4 in there is just naming those parameters. So I'm naming the error variance for Y1 to be T1. I'm naming the error variance for Y2 to be T2. I'm naming the error variance for Y3 to be T3. And I'm naming the error variance for Y4 to be T4. And I'm doing that because I want to do that little computation later. To do the phantom variable trick, I don't actually need to name those parameters. But if you want to do the computation of the reliability the way that I showed you, you need to name the parameters. Yeah? Good? Okay. All right. For those of you who don't remember the formula for Chromebox Alpha, here it is. So just to remind, and you were thinking, what the heck does this mean? So, and I should say too, that often when you fit the reliability estimate, for the tau equivalent model, you might get something akin to Chromebox alpha. But again, if you're, there's no guarantee that you're going to that you're going to reproduce Chromebox alpha, because it's done in a different way. And especially if you're not meeting all of the assumptions of, like, if you're meeting all of the assumptions of Chromebox alpha, if you have a tau equivalent model and you estimate the reliability in the way that we're talking about, then you should basically reproduce Chromebox alpha. But if you're not meeting the assumptions, then the sort of the computation of Chromebox alpha this way is not necessarily going to give you the same thing as the computation of alpha under the tau equivalent model in the latent variable modeling framework. Often it will, very often it will, but it isn't a case where it has to. It's like not a oh, this is definitely going to give you the Chromebox alpha estimate. Okay, so let's unpack what this Chromebox alpha formula is telling us here. So what the heck is on the top and what the heck is on the bottom? So the top is just saying, take the sum of the item variances for all of the items on your scale, okay? And the bottom is saying, take the sum of all the item variances and covariances, because the total variance for a scale is actually the sum of the item variances and covariances. This is kind of a cool thing. So like you have variance covariance. And let's say my covariance is so this is you can see variance covariance matrix all one level. So this is my variance covariance. You want to know what's the total variance in this. I know this is what the total variance on the scale actually the sum of all the elements in variance covariance matrix. How do I get the sum of all the elements? Well, I need to actually take out both sides of the diagonal. So when I say the sum of all the elements, I literally mean the whole square. So in that case, I can get by taking the sum of the variances diagonal plus 2 times the sum of the unique. I say unique here, I don't mean like uniqueness here. I just mean, remember, the same thing's always above and below the diagonal. So you could just whole thing. You can matrix that's in Excel. You can literally just take the whole thing and just say, now what's the sum of this matrix? Right? That will actually give you the sum of the variances plus 2 times the sum of the unique covariances, or equivalently, the sum of the whole covariance, whole square. That's what this is. On the top, this. These are actually the item variances. So what this is saying is on the top, sum those diagonal elements, sum the item variances. And then why is it 1 minus that? Anybody know? And this is a place where like the formula is kind of silly, because really there are lots of different formulas. looking at, what we're really looking for is like the shared variance, which is actually the sum of the covariance. But if you think about it, if I take 1 minus the sum of the variances over the total, that actually gives me the sum of the covariances over the total. So an alternate formula for this is actually just to say, take the sum 2 times the unique covariances, right? So you're summing all of the diagonal elements, both above and below the diagonal, and divide that by the sum of the whole matrix. And that is actually what this is. And so it's really giving you like the shared variance on the top divided by the total variance across all the items on the bottom. Then that is just multiplied by k over minus 1. And k here is just the number of items on the scale. So, when we have a four item scale, it's going to take whatever this whole thing is, multiply it by 4 divided by 3. That is how you compute black delta. So, I think it's kind of, when you start thinking about it as the elements in the matrix, I think it actually starts to make a lot more sense than just sort of thinking about the formula. Because, thinking about the formula in that way makes more sense, I think. Okay. Oh, good. I thought that wasn't going to disappear. Okay, last but not least, the parallel model is our most restrictive measurement model. And this really is assuming that the test items are equivalent to each other. Because think about what we're saying. We're saying that the item is equally predicted by the factor, right? So it has, again, in measurement terms, it has equal discrimination. It's an equally discriminating item. All the items are equally discriminating. And I'm saying that the errors are the same. So I'm really saying that they're, these things are measured with the same degree of precision and the same amount of error. Now, the one thing that we're not looking at here, which would be another thing you could look at, we're not going to do this today, would be actually to think about equality of intercepts, right? If you really wanted two items that were truly interchangeable with each other, then you would also constrain the intercepts to be equal. A parallel model doesn't say that the items are like exchangeable with each other in the sense that they have equal difficulty. It's just that only the difficulty varies, right? Everything else about the item is the same. They're equally predicted by the latent variable. They are measured with the same precision. They have the same amount of error. And so the only thing that's really different about the items is that one item is more difficult than another. And if you have a set of items that are parallel like that, then you can sort of pick and choose items with different difficulty levels, but that are the same in every other regard to build a really kick-ass test. And that's what test developers do. That make sense? So we're not constraining the intercepts here. Again, you could do that. What that would mean is all of these items are basically, in some sense, redundant, right, at that point, because they have the same, they're equally predicted by the factor. Not that they're the same item, but their characteristics are totally the same. So they're literally two items that have equal intercepts that come from a parallel model could be exchanged for one another in a test, right? I could use that to create two tests, like how there used to be alternate forms before computer adaptive testing. Now you would use two items that are in computer adaptive testing. You could sort of have this bank of items, but you could say, okay, well, these items, they're equally difficult, they're equally discriminating, they have an equal amount of precision and error variance. So basically, I could exchange this item for this item on the test, and I should get the same results, right? That's the idea. All right, but again, parallel model doesn't assume equal difficulty. That's the only parameter we're really letting vary. Okay, so again, So for the parallel model, the important thing here is that I'm going to constrain the error variances to be equal to each other. So I'm constraining the factor loadings to be equal to each other, and now I'm constraining the error variances to be equal to each other. So, for example, here's a code. So the only thing that really looks different here is that down here where I say y1 to y4, I'm now constraining, I'm now constraining all the error variances to be equal by saying, I just call them EV for error variance. They're all going to be equal. Yeah? Okay. Now, there's another kind of reliability that people compute in SEM world called coefficient H. And coefficient H is like the maximal reliability. So it's the, you can think of this as like the proportion of variance of the construct that's theoretically explainable by the indicator variables. And this tends to be, again, sort of, I didn't say optimistic, but it is maximal reliability. So this is going to tend to be a sort of a high estimate of reliability. So coefficient H is actually something you can compute really easily by hand, or again, you can set it up in the constraints in M+ after you've got the model. It's not going to fall out quite as nicely with our little trick, but what we do is we need to take the so this is important. You got to use standardized loadings for this, not unstandardized loadings. If you use unstandardized loadings, well, if you think about the math here, if you use unstandardized loadings and the loadings are above 1, bad things will happen with this formula. So you definitely need to use standardized loadings. So here, what you're doing is you're basically taking the standardized loading for each item, and you're dividing it by 1 minus the standardized loading for the item. So think about, like, if the standardized loading for item 1 is 0.9, let's say, you're taking 0.9 squared, which is 0.81, divided by 1 minus 0.9 squared, which is 1 minus 0.81, which is 0.19. So it'd be like 0.81 divided by 0.19 would be for the first item if it has a loading of 0.9, right? Plus, now let's say the next item has a loading of 0.8, so it's going to be 0.8 squared, so 0.64, divided by 1 minus 0.64 is 0.36, so it'd be like 0.64 divided by 0.36. You're going to add that to the first one, and you're going to keep doing this for every item that you have. So it's every item, you take the squared loading, you divide it by 1 minus the squared loading. And if you think about that formula, obviously, the closer the loading gets to 1, the bigger that term of the squared loading divided by 1 minus the squared loading is going to be, right? So that's one way that this kind of gets bigger, right? And then, so you're going to do that for all of the items in the numerator. And then you're going to do the same thing again in the denominator. But notice that in the denominator, it's the same as the numerator plus 1. Right? So there are sort of two ways that this maximal reliability gets big. One is by having one or more high loadings. Like, the more high loadings you have, obviously, the bigger it's going to get. But if you think about it, even having, just a small number of really high loadings is going to kind of drive this thing to get actually pretty big. And then the other thing is by having a lot of items, which of course we said that reliability is a function of not just the inter-item correlations and stuff, but also the number of items. And so the more items you have, again, because this thing is repeated in the numerator and the more items you have, sort of the bigger that term is going to be. And then it's that term divided by 1 plus that term. So the more items you have, sort of the bigger the maximal reliability is going to be. Yeah. Like in what context? Yeah, I'm just saying, like, the higher, again, if you think about like just imagine, if you take 0.99 squared divided by 1 minus 0.99 squared, like think about that. That's like what? calculate. It's like something really huge, right? Because it's almost 1 divided by, well, 1 minus 0.99 squared is divided by almost 0, right? So like, I don't know that I have a rule of thumb, but what I would say is the closer the bigger the loading gets, the more that term, that sort of, that ratio or whatever, that fraction, the bigger the loading, the bigger that's going to get. And what I was saying is, even like, you can imagine a situation where maybe a bunch of the loadings are small, but you have one ginormous loading that's close to 1. And because that one loading is close to 1, it's going to blow up one of those numbers to be really big. And then remember, you're taking that thing divided by that thing plus 1. So even one really large loading can drive this maximal reliability to be very high. The other way you can get the maximal reliability to be very high is just by having a whole ton of items, and then anything in between, right? So I guess that's what I would say about that. I always feel like this isn't fair, right? Because I'm sure that Greg Hancock, this is his measure, would probably, like, I don't know, disown me. Well, he doesn't own me, but he would be very upset if he heard me saying this. But like, I always think of this as the very optimistic estimate of reliability, like, yeah, maximal, like, as good as it's going to be, but I don't know. So that's coefficient H. It does come in kind of handy. Hold on, before I say why it comes in kind of handy. This is a slide that you probably don't remember from week 2, because I think we just skimmed right by it and talked about it for maybe 5 seconds. But it's going to be important now if you want to compute coefficient H. It's only important if you want to compute coefficient H by putting constraints in M+. If you want to just take the standardized loadings out of the output, put them in Excel, and square them, then you don't need this. But if you were to say to yourself, hey, I want to write a formula like you did for the other reliability to compute maximal reliability, then here's the problem. We can name parameters, right? But think about it, when we name the loadings, we're naming the unstandardized loadings. There's no way to name the standardized loadings, right? So that's okay though, because I can very easily compute the standardized loadings from the unstandardized loadings. So if I name the unstandardized loadings, I can compute the standardized loadings. So let's remind ourselves, like, how are the standardized loadings a function of the unstandardized loadings? This is a good review anyway. So to get the standardized loading, you just multiply this. It's just like, again, this is totally analogous to how do you get a standardized regression coefficient in regression, right? It's the same thing, except for, now we're talking about, we've got a factor instead of, right? We've got a factor and an indicator rather than an independent variable and a dependent variable. So the factor is like our independent variable, right? The indicator is like our dependent variable. So we're going to take the unstandardized loading and we're going to multiply it by the standard deviation of the factor divided by the standard deviation of the indicator. And when I say the standard deviation of the indicator here, I do not mean the error variance. So I'm not talking about when you look at the output and it says x2, and that's the residual variance of x2. I'm actually talking about the total standard deviation of the indicator, the thing that you would get out of your favorite computer program. Or, again, you don't have to get it out of your favorite computer program, because if you ask for stat from M+, it will give you a variance covariance matrix, right? And of course, the standard deviation of the indicator is just square root of the variance of the indicator. So if you want to get standardized loading and you have the unstandardized loading, you can just take the unstandardized loading. In this case, we're constraining the variance of the factor to be 1. So we don't even have to worry about the standard deviation of the factor because it's going to be 1. We can just take the unstandardized loading and divide it by the square root of the variance of the indicator. And again, I'm talking about the square root of the variance of the indicator that comes from the sample statistics, not the square root of the error variance of the indicator, but the square root of the entire variance of the indicator. Does that make sense? Okay, so I think I have some code that shows how to do that. Here, actually, I do have code that shows how to do it here. I also have it in our example. So I broke this out more than you actually need to, just to kind of make it, I'm afraid to look at the time. Oh my God. Just to make it easier to look at. So here I'm saying like SL for me is standardized loading. So I'm saying new, and I'm creating 4 new parameters. And those are standardized loading 1, 2, 3, 4. And you can see that I take standardized loading 1 and it equals the parameter B1 is just the parameter value for the unstandardized loading divided by the square root of the variance for that item, which again, I got these numbers from the variance covariance matrix that I asked for from sample statistics. Or I could just, run something in R or SPSS or whatever to get these, if you do that, you could just get the standard deviations, then you wouldn't have to take the square root. But I was using the variance covariance. Yeah, I'm sure that's not important. Notice my daughter did not call today, right? On the way out the door, I was like, or actually it was last night because I left really early. Don't miss the bus. Anyway, so that creates the standardized loadings. And then I want to compute this coefficient H, this maximum reliability. So I call that max H. And I mean, maybe I shouldn't have called these S1 to S4. I had some logic for why S made sense. I forget what it is now. It's sort of close to SL, so that's unfortunate. But S1 to S4, here I'm just taking the, I think I was thinking the squared loading divided by 1. So I think it was for me, this was the squared loading. So notice that I'm taking the squared loading, so the squared standardized loading, so that's SL1, and I'm squaring it, and I'm dividing it by 1 minus the, SL1 squared, right? And I do that for each of those. So I do S2, S3, S4. And so I've got each of those terms. And then once I do that, I can just compute max H, which is just going to be S1 plus S2 plus S3 plus S4 divided by 1 plus S1 plus S2 plus S3 plus S4. Again, you could write this way more compactly. You could probably write it all in, far fewer lines. I just thought it might be easier to sort of break it out like that so you can see exactly what's going on. But that'll give me the maximal reliability. You want to compute it in M+. I think for your homework, I asked you to compute maximal reliability. You can choose. You can either write the code to have M+ compute it, or you can just look at the output and take the standardized factor loadings and square them and compute it that way. Totally your choice. Oh yeah, sorry, I should have said that. So that is a new thing, no pun intended. So new means that, new is any of these parameters that I didn't name above in the model command. So remember, in the model command, I named B1, B2, B3, B4. So when I come down to constraint, I can just use them because I've already named them. But if I want to create a new parameter, then the first thing I have to do in M+ is I have to tell it I want to name a new parameter. So first I say, here are the new parameters I want to create. And so that kind of creates these buckets for the new parameters. And then I go through and I define what those new parameters are. So if you tried to run this code without having new, it would be like, I don't know what SL1 to SL4 are, but that's because you didn't tell it. So you just have to tell it what you have to, you don't tell it, you just tell it that you want those. And then the other thing to just be aware of is that you have to something plus. It's not going to like that. It'll have to be 1 minus 1. Always wanted sort of algebraic. What's on the left-hand side of the equation? Not really thinking about it. And then, I try to run it. It's like, no. One thing on the left-hand side of the equation. So just be aware of that. And you sort of need to structure the constraints appropriately. All right. Yes. Sure. No, well, right now it's not the square root. It is the variance of item 1. Total variance of item 1. So it came not from the model stuff. Right? If you take stat right in the front, you'll get the estimated variance covariance matrix. It comes from there. Or again, if you happen to know what the standard deviations of those items are from before, you can just use those, and you can just it's taking the square root to get to the standard deviation. Yes. Where's so the B1 is, so the B1 is the factor loading, right? So the first thing I'm doing is I'm taking the factor loading. That gives me factor loading. Here, I'm taking the standardized loading minus the square. Get those pieces that I needed for the So what I said is, because I fixed the factor variance to 1, I don't need factor variance. You are right, though. If I wanted to create a standardized loading in general and I had a factor variance that isn't 1, then I would take, for the standardized loading, it would be unstandardized loading multiplied by the standard deviation of the factor divided by the standard deviation. Right? And so in that case, you would take the factor variance and you take the square. In this case, we don't need that because we fixed our factor variance to be 1. But that is true that in general, the standardized loading is the unstandardized loading times the standard deviation of the factor divided by the standard deviation of the indicator. Any other questions? Good. All right. So, so again, coefficient H really tells us about the proportion of variance of the construct that's theoretically explainable by the indicator variables. It's bounded by 0 and 1. It's going to be, if you look at the formula, because we're squaring everything, it's unaffected by the sign of the loading. So if you have some negative loadings and some positive loadings, you don't have to worry about that. Unlike Chromebox alpha or other estimates of reliability, like you better make sure you reverse score stuff before you compute a reliability estimate normally. But in this case, because we're squaring everything, right, the sign of the loading doesn't matter. So we don't have to worry about reverse scoring before we estimate this. And it's always going to be greater than or equal to the reliability of the strongest indicator. And again, we sort of talked about that formula and how, if you have a really, really strong indicator, right, that's going to sort of drive the boat. So the way that it's sort of set up, it's always going to be at least as high as the reliability of the strongest. All right. So one thing that's really nice about coefficient H is that you can use, and you can do this, again, you can compute this just using data from other people, right? If you're looking at somebody's, let's say, published a factor analysis of a scale, and you know what the loadings are for the, for that subscale, you can actually use those standardized loadings to compute coefficient H by hand. It's really easy. And then you can use this as a placeholder for the measurement model of each factor in a latent variable model. And what I mean by this, and we're not really going to talk too much about power in here, but like, just say you wanted to run a power analysis. Let's say you don't have any data yet, and you want to run a power analysis, and you've got a latent variable model. So one of the things that you have to consider, obviously, is, you know, what is the sort of strength of the path that you're interested in? I mean, that's sort of regular old power analysis, right? Like, how big do you think this path is going to be? How well is, you know, group or whatever it is going to predict whatever, right? Okay, fine. So that's sort of your regular old, maybe that's your effective interest. But the reliability of the factor is also going to come into play when you start to think about power. And actually, there are sort of two different, I don't want to get too much into power right now, but there are sort of two different things to think about when you're thinking about power for structural equation models. Well, at least two things. One is sort of the power to detect misfit in the model as a whole, right? You remember we get that overall chi-square, and we could be asking ourselves, is my, you know, am I sort of adequately powered to detect, you know, right, to sort of detect misfit or whatever, sort of in the model, like the model as a whole. Is the model as a whole kind of adequately powered? But then we could also be interested in like focal parameters of interest. Like I'm really, this is really the parameter of interest in my model. This is really what the whole study's about. And I want to know, am I adequately empowered to sort of detect, you know, that this path is not zero, or that the, you know, the difference between two groups is not zero, or whatever it might be. But the reality is that the reliability of the measurement model actually impacts the power that you have to detect effects. I mean, it makes sense if you think about it, right? So, you know, higher reliability equates to more power, as you might expect. So often, you might be like, this is just a really simple example, but like, you might be saying, okay, I want to do like a power analysis, and I want to kind of think about, you know, the power to detect, maybe I'm really interested in thinking about the power to detect these effects of interest, but like, I've got latent variables. All my variables are latent variables. So to do the power analysis, I really have to do the power analysis for like a latent variable model. But I mean, I don't want to make a guess about every loading for every latent, like I've got, you know, each of these latent variables, maybe it has 10 indicators and I don't have data yet. So, and I, you know, but what I can do is I can take coefficient H and I can basically use that as a placeholder and sort of like do a power analysis with kind of like a single indicator where I'm sort of saying, okay, I'm going to use this estimate of reliability to give me a sense of like what the reliability of this latent variable will be. And then I can use that, and then I can actually get the power analysis that's more appropriate because I've sort of taken into account the reliability of the latent variables. That all went over your head. Don't worry about it. That was enrichment. But I mean, this is why power analysis in SEM is like really hard. Because, well, first think about how many parameters. Power analysis for what? What parameter are you interested in? But also, you need to, so there's that. And or is it the model as a whole that you want to make sure is adequately powered? But then beyond that, like once you have latent variables, you really need to take into account the reliability of the latent variables in order to get a good estimate of power. And so this is where coefficient H can come in handy. It can give a placeholder for the reliability of the latent variable that you can use when you're sort of a priori just trying to do a power analysis. All right. Oh, this is a good place for a break, I think. Yes? Go ahead. No, we'll do questions before the break. Well, you go back to somebody else's data. Yeah. No, like you've probably got some idea. Somebody else has used the scale and they've got an estimate of the reliability, right? And that's the tricky thing about power analysis in general. Like, I don't know, such a big guess. Yeah. Oh, do you mean like checking the reliability? Well, I don't know how you would do it before you build the measurement model. I think you would do it like I guess, sort of simultaneously or right after. Like you build the measurement model, then you check the reliability, right? So because you can't really do, like you need to build the measurement model to check the reliability, and you need to check the assumptions in the measurement model to sort of know, right? So I mean, I would say you start off by, you start off with your unidimensional congeneric model. You then maybe want to see, can I make the assumption of tau equivalence? Yes, no. If I can't make the assumption of tau equivalence, then I'm going to be way better off computing and reporting coefficient omega than coefficient alpha. If I can make the assumption of a tau equivalent model, then probably fine to report Chromebox alpha. The reality is, though, that like most people who report Chromebox alpha do it because they don't know any better, not because they actually checked all the assumptions and discovered that it was a tau equivalent model, right? So you're going to be more savvy about it now. You're going to check your assumptions. Does that make sense? But yeah, I would say, right after, like simultaneously with. Questions before we take like a 10-minute break? We'll come back. I will show you how to do these measurement models quickly in M+, and then we'll talk about equivalence nesting. Yeah. Sure. About which homework? This homework? The one that's coming up or the one that you're just are doing? Yeah, right after class is good. Or at the end of class if we have time, but realistically, how likely is that? Okay. I think I did not upload the homework yet for this week, so I'm going to go do that right now.
thing in my fingers like pain.
All right. So here we go again. You should have, I put in the courses folder some models for the measurement models, the congeneric model, tau equivalent model, parallel model that we can run through. And you should have an annotated output here that actually walks through a lot of the computations, which I hope will help. So on that note, let's see, let's start with the congeneric model, which I already pulled up. So you'll find it in the courses folder under, I don't know what it's called. I forget, what was the folder called in there? Reliability. There we go. That's what it was called. Reliability. Okay, so the first model we want to look at is the model that says, oh, and let me make this bigger. Have a what? Change. Point maybe. Okay, that's better. Okay, so here we go. So the first model, so you should have the annotated output right, and the models are also available on the courses or in the Husky CT. So I've kind of walked through, I mean, I feel like we've kind of looked at this code already, so it's probably pretty obvious. But we've got, our file. In this case, our file has is a correlation matrix with standard deviations. So I'm telling it type is STD and core, STD core, so that it knows that standard deviations and correlations. Number of observations is 500. And then we're using the first 4 variables in this data file. And again, we start by specifying a fixed factor model. And then we are freely estimating the factor loadings, but I'm actually giving them names. I'm giving the factor loading parameters the names B1 to B4. And then I'm giving Y1 to Y4 are the error variances for those 4 variables, and I'm naming those T1 to T4. So that just names the parameters for the error variances. I create my phantom variable by saying X by and then X at 0. So this creates my phantom variable. And then I need to regress X on those 4 indicators. And there I'm constraining each of those paths to be equal to 1. So it's X on Y1 at 1, X on Y2 at 1, X on Y3 at 1, X on Y4 at 1. And then you can see I did put in the model constraint. I created a new parameter called reliability. And reliability here is just, the B1 plus B2 plus B3 plus B4. Those are the 4 loadings. I sum those loadings and I square them. And then I divide that by the sum of those loadings squared plus the sum of the error variances. And that will give me an estimate of the reliability as well. Okay, so that's my code. I can run this model. Bigger now too. Not that that actually causes any problem here per se, but got that earlier. Okay, so here's where I was talking about getting the sample statistics. If I need if I want to get the variances for the observed variables, here are the variances for the observed variables. And then here's my chi-square, degrees of freedom, et cetera, et cetera. So you can see in this model, I mean, we only have four, yes. No, I missed a parenthesis. I don't know this one. Is that right? There are 3 on this side, right? Because it's 1, 2, 3. I think that's the problem. And then 1, 2, 3, 4, 5. 1, 2, 3. I think that's okay. Luckily, if you have an extra parentheses, it runs okay, but it tells you that you messed up the parentheses. Now, if you don't have enough parentheses, things can go badly for you. No, this is matching right parentheses. Okay, hold on. Right matching parentheses. What? Of this one? Probably. I'll go with that. That makes sense. It shouldn't have 6. Okay, let's try. I don't see that error anymore. All right, cool. So now we're good. All right, so you can see same output. We've got 2 degrees of freedom. 3.976 is my chi-square. So actually, I mean, again, it's a really tiny model, right? I only have 4 variables. I only have 2 degrees of freedom, but the model does seem to fit pretty well. So that's nice, right? Okay, so the congeneric, but again, this is like the least constrained model because I'm not constraining the loadings to be equal or anything like that. But this model seems to fit pretty well. If I look at the results, okay, these are the unstandardized factor loadings. What do you think? When I constrain those to be equal, do you think the fit will get worse? Yeah, I think that's a fair bet, right? I mean, they range from 0.886 up to 2.68. Remember, the next model, the tau equivalent model, is going to say all those loadings need to be equal. So, I mean, I feel like we can see right now, even though the congeneric model fits well, there's definitely some indication here that the tau equivalent, I would expect, based on my results here, that the tau equivalent model is probably not going to fit so well. On the other hand, if all of these unstandardized loadings were all in the 0.8s and 0.9s or 0.9s, if they were all kind of close to each other, then I would think, oh, well, that might actually work out for me, right? And then you can see here are my residual variances, which also don't really look the same, but in some sense don't look as different from each other as the loadings do. Okay, and then you can see again, this is my phantom variable. So this is really like nothing interesting is happening here. I constrained all those loadings to be 1, right? And remember, I mean, if you haven't figured this out yet, I don't even know if I said it explicitly, but when you see that 999 there, that's an indication that that's something you've constrained, right? See how it says like 1, 0, 999, 999. That's because you constrain those things. You're not getting any kind of standard error or p-value. Okay, so everything there is constrained. The factor variance is constrained. Here are my residual variances. The residual variance of x is constrained to be equal to 0. Remember? And then here, I remember I wrote out a formula for the reliability in my constraints. And so here is the reliability estimate. But remember that I did this trick so that I could actually get the reliability in an even easier way. And so if I, here are my standardized loadings, by the way, which don't look as different as my unstandardized loadings, but they still look pretty different. Come down here. One of the things that's nice here is that with the confidence interval, I actually get a confidence interval for my reliability, which is great. So I don't just get the reliability, but I get the confidence interval. Okay, but now remember, I want to know, I just passed it. Here is the oh, it might not be on your printout. Sorry about that. It is not. I think I added that code later. But you just say the interval, right? And then here's the confidence interval. So this is the 99. You always have to be careful and look up top because there are so many columns. But this one and this one, the 99% confidence interval, see lower 0.05 and upper 0.5%. This and this give you the 95% confidence interval. I'm looking at the residual variances now, reliability, but same idea. And then this is going to give you the 90% confidence interval, and then the estimate is right in the middle. That's how the confidence interval output always looks. So if we scroll down to the reliability, go. Standardized, that's why. Here we go. The reliability, this new parameters thing is going to show up at the end of the unstandardized output. So I always do this. The very first time I look at confidence interval output, I do a double take. And I'm like, oh yeah, that's right. It's not. It's the lower bound of the 99% confidence interval. I need to look in the middle. 0.92 is my reliability, which we saw that above, right? And then if I wanted a 90% confidence interval, it's basically 0.91 to 0.93. If I wanted a 99% confidence interval, it's basically 0.90 to just under 0.94. So no matter how you sort of slice it, that's pretty good reliability. I can feel good about that reliability estimate. Now let's look at, though, I did the phantom variable approach so that I could, get the reliability even more easily. So for that, I have to ask for tech4, which is going to give me my estimated covariance matrix and estimated correlation matrix for the latent variables. That's what tech4 does. So here it is. And what I'm going to do is I'm going to look at the correlation between the factor and that scale score, that phantom variable that I'm using to create the composite. And notice that the correlation is 0.959, right? The calculator. There we go. So if I go 0.959 and I square that, I get 0.92, which is exactly what we got as our estimate of reliability. So one way to get the reliability is to sort of build that whole formula for reliability. Just to actually approach and get correlation, but the important thing is here it's correlation between the true score and that observed scale score. So you're going to need to square. Once you square it, this number is going to be exactly the same as the number that we saw when we computed it. Right? All right, cool. It's always good when things triangulate. All right, so now I feel good about that. My congeneric model is awesome. And that means actually, I mean, again, I only have 4 variables. Not that interesting a model, but like I can feel pretty good about unidimensionality here. I think my four variables are probably pretty unidimensional, probably don't have major correlated error problems, right? Because this model fits actually quite well. But now let's try for a tau equivalent model to see if, because again, if the tau equivalent model fits, then I can report Chromebox alpha. So now let's fit the tau equivalent model. Okay, so if we go in open. Oh, actually, no, before we do that, and I don't have this on your output. So I apologize for that. But here is the code that I used for getting that coefficient H, the maximal reliability. So let me just point out a couple of things. The first is that I get rid of the whole phantom variable thing. That's just gonna kind of muck up what I'm trying to do with coefficient H. So I'm still going to run the same model. I don't have the phantom variable thing here. I've got the model constraint stuff that we actually talked through. Right? Are those the right? I don't think those are the right variances. They're not the right variances because I stole this from, I was playing around with the second factor. Okay, so we need to change the variances here. So somebody read me out the variances from the sample statistics output. Well, we had it before. Okay, hold on. I'll run it again. Well, we have it. We have the output right here. Oh, can't open the output. Why it doesn't recognize M+, I don't know. So annoying. M+. Here we go. Open up the output. Output. Generic. Okay. So it's 1.322. Okay, 1.322. 1.440. 2.465. And 7.952. Yeah, this is such a wonky example, by the way. This is an example where Chromebox alpha doesn't actually converge that well with the other reliability estimates, but I mentioned that Y4 is kind of funky. All right. All right, so save. And of course, we don't meet the assumption. Okay, so let's see. Those are right, right? They look good. They look good to me on that. And now, when I run this model, I'm going to get the same model fit, of course, because it's the same model. And here we go, new additional parameters. Oh, this is the downside of doing it the way I did it. I made so many new parameters. You got to find your max H in there. But here it is. So my coefficient H is 0.934. Now notice that is higher than the other reliability estimate that I got. But remember, I said that this coefficient H is like a maximal reliability. It's not going to necessarily be the same thing as the reliability estimate that you got from the congeneric model. And it's going to be higher, you know, generally. I always hesitate to say absolute 100% terms, but I might be able to say it in 100% terms, but it's certainly fair to say generally without question. So I think, yeah, I can't think of a case where it would be lower, but anyway, so that's my maximal reliability. Again, the other way to get the maximal reliability, oh, well, let me show you something here. So here are my unstandardized loadings. Remember, we saw those before. 0.886 to 2.683, right? And now look at these. These are my standardized loadings. that I computed as part of the model constraints. So 0.771, 0.799, 0.758, and 0.951. So let's go down here. Okay, they're within 1,000 the decimal place, which again, you know, we only have things to 3 decimal places here, so they're not going to be spot on, but they are super duper close, right? Super duper close. If I had more exact estimates of the variance and more exact estimates of the loading, I could get them to be spot on. But remember, M plus is using things to umpteen decimal places, and we only really have 3 at our disposal. Yeah. What? It's the maximal reliability. What did you say about the minimum? Oh, I said it won't be lower than the reliability of the highest indicator. That minimally maximal, this coefficient H as the minimum of its reliability would be the reliability of the strongest indicator. Oh, you're talking about that picture. Yeah. Where do I say that? I don't. So I would say coefficient H is a pretty optimistic estimate of reliability. What I'm saying in that second bullet point is if you're trying to do a power analysis for models with latent variables, you want to put in as a placeholder something that's a good estimate of the reliability. Or what I put in there for minimum, I was sort of saying, like, if you wanted to be conservative in your power analysis, you might want to put in a lower estimate of reliability. But I did not, and I can totally see where that's confusing, but I did not mean to imply that coefficient H itself is a minimum estimate of reliability. Coefficient H is a decent estimate of reliability, but I'm just saying, like, placeholder. And, you know, the placeholder is the anticipated construct reliability. And then in parentheses, I should take out that or minimum because I can see how it's super confusing. But my point was, like, always with a power analysis, you want to go conservative. So, you know, if I got a coefficient H of like 0.95, I might not use 0.95 as the placeholder. It's what I was thinking and trying to say. I might like move it down a little bit just because I think of coefficient H as being optimistic. And I might be like, 0.95, that seems crazy high. Maybe I'll call it 0.9. I feel like maybe that's more, you know, because again, I'm just making it up. I'm just like plugging in a number in a power analysis. So I'm sort of saying, so in my mind, you start with coefficient H, you look at it, you want to be really optimistic, you use it. If not, maybe you like adjust it down a little bit. But it at least gives you a really good starting point as a placeholder for the construct reliability. Does that make sense? Yeah. That whole slide is really about, like, what would you do for power analysis? So sorry about that. I totally see where that was. Okay. In fact, I'm going to make that clarify that after. Okay, so anyway, though, you can see how we got the same standardized loading. So that's good. That's a nice check, too, that we can get our standardized loading. So now let's see what happens if we run the tau equivalent model. So if we open tau equivalent 2, not the one that says test, but the one that says 2. Okay. And so we've kind of looked through all of this code already. You know, I built in the model constraints. I've got, again, I sort of built it in pieces here where I say, like, I'm going to create reliability. This is the true score variance. This is the error variance. And then reliability 2, actually, so reliability just does everything in one big swoop. I should probably check make sure we don't have too many. No, that one actually looks right. This is probably the one I corrected the parentheses on, and I didn't correct it. I know I corrected it on one of them. And then, oops, this should have a, because at the end it won't matter, but so reliability and reliability 2 are going to be the same. One I just did in pieces, and the other one is just the whole formula in one fell swoop. Any questions about the code on this before we run the model and look at the output? I mean, I feel like we kind of looked at this code before, so I think it's relatively straightforward. So let's run this. Okay, at first, let's look at our model fit. And remember, I saw that the loadings did not really look equal. So how bad is it? Okay, well, I've picked up 3 degrees of freedom, which makes sense because now I'm only estimating 1 loading instead of 4, right? So that's 3 degrees of freedom. So now I have 5 degrees of freedom. My chi-square jumped up from, what was it? It was 4, basically. And now it's 417. So I think this is a no-brainer that this tau equivalent model does not fit, right? And given that we ran the congeneric model, and we know the congeneric model fits well, it's not necessarily a problem with unidimensionality, correlated error, right? Like we know what the issue is. The issue is constraining all these loadings to be equal. Okay, so anyway, but this is the tau equivalent model. The fit is not good, but be that as it may, let's go ahead and just look at the reliability estimate. So let's start, actually, let's go down to the bottom here. Let's go to our, okay, here it is. The estimated correlation between the latent variable and the X, sort of the composite variable. And notice it's now 0.859. It was like wasn't it like 0.959 or 0.96 before? Right? But you can see that the estimated correlation, like now that I'm constraining all of these loadings to be equal, I'm actually finding a lower correlation between the latent variable and the composite variable. And so when I square that, I take 0.859, and I get 0.738. Now, again, this 0.738 is the sort of the estimate, this latent variable estimate of the reliability, assuming tau equivalence. This is not necessarily going to be the same thing that you get when you estimate Chromebox alpha. Often it's very similar. Sometimes it's not. In this particular example, it's not. I think but if you look at which is why I was playing around with factor 2 earlier, if you look at factor 2, it's very, very similar. But there's just some wonkiness about the Y4 variable in terms of the amount. It's got like, remember how we saw the variance was like 8 or something? And the factor loading, I mean, there's some wonkiness in Y4 there that is when we're constraining all the loadings to be equal, things just go a little haywire. And so now the estimate of this latent variable reliability computed in this way drops dramatically. And of course, I shouldn't compute, so it's not the same as Chromebox alpha, but I also shouldn't compute Chromebox alpha because I for sure am not meeting the assumption of tau equivalence, right? So really, what should I do? Well, I should not use this model, right? Like I don't need to perseverate about what's the right reliability estimate for this model because this is the wrong model. I should go back to the congeneric model and I should use the reliability estimate that came from there because this model is bad. It's severely misspecified. And so I can't really trust a reliability estimate that comes from this model. But again, remember, Chromebox alpha makes the assumption of tau equivalence, so I probably shouldn't be computing Chromebox alpha either. Is everybody with me? Does that make sense? But it is interesting, like the reliability estimate here is radically different from the one that we got for the congeneric model. Again, that's not always going to happen, but it certainly happens here. Questions about that? So obviously, there are things we do in this class, because it's a class, that you would never do in real life, and that's the next model. Clearly, the parallel model is not going to fit because the tau equivalent model was horrible. But, just for the sake of completeness, and because, we're going to run the parallel model. There's actually something kind of interesting that happens. But so let's run the parallel model. But again, so if for homework I ask you to do this, you would do all three models. But in real life, if you found that the tau equivalent model was that bad, the parallel model, because it's even more constrained, the chi-square can only go up. The fit can only be worse. The fit can't get better, right? So, okay, let's do it. So let's go to our parallel model. Parallel, it is model number 3. So again, you can see that the big thing here that's different is, really in the front part of the code, the only thing that's different is that I'm now, instead of naming the error variances, what did I call them? T1 to T4 or something. Now I'm just naming them EV for error variance, and I just have 1 error variance instead of 4. So I'm going to pick up another 3 degrees of freedom. So I'm going to go from 5 degrees of freedom to 8 degrees of freedom, right? And now you can see actually look at how much simpler my formula is for reliability now, right? Because I'm, I've got B1, I've actually constrained all of the loadings to be equal. So I could do this with the tau equivalent model too. I constrained all the loadings to be equal. So instead of saying like B1 plus B1 plus B1 plus B1, I just said 4 times B1 because all the loadings are equal. And then I square that, right? And then in the denominator, I do that again. I say 4 times B1 squared plus, and I do the same thing here. The error variances are all equal. So I could say EV plus EV plus EV plus EV, but they're all the same. So I just say 4 times the error variance. So that's why the 4s are there, because multiplying by 4 is the same as like adding the same number 4 times, right? All right, and then ask for STDYX and Tech 4. Fine. Go ahead and run this model. Right. So first things first, let's go down to Tech. Let's look at fit first.
Unknown caller.
Oh, thanks. Okay, there we go. Okay, well, I thought my fit couldn't get worse because it was like 400 and some, but constraining these error variances to be equal, my chi-square is now 1031. And look at how bad my TLI and my CFI are. It's rare to see TLI and CFI that are that bad. Now, remember how those work. They're incremental fit indices, remember? So they're kind of putting where your model is on you can sort of think of them as putting your model on sort of a continuum between the worst possible model, which, by the way, is sort of indicated from the, the baseline or the null model chi-square, and the best possible model. And so, you can see, although the way, actually, this baseline model is not necessarily the exact baseline model you would use for the TLI, but you can see that 1031 with 8 degrees of freedom, that's horrible. That's absolutely horrible. And actually, we are way closer to the worst possible model than the best possible model, which is why our CFI and TLI are so incredibly horrible. And our RMSEA, it's rare to see an RMSEA above 0.5. So that's really bad. All right, be that as it may. What is our estimate of the reliability? Well, let's go down to, let's start with our Tech 4 output correlation matrix. Now, this is what I said is kind of interesting, I think. I don't know. Don't ask me why exactly, but what's really interesting is notice that the reliability now is 0.917 squared, right? So 0.917 times 0.917 is 0.84. So the reliability estimate for the parallel model is actually better than the reliability estimate for the tau equivalent model was. But again, it's just weird, but don't make too much of that because you can't trust this reliability even more than you can't trust the last reliability because this model fits even worse than the last model. So again, we're not trying to pick a model that has the best reliability. We're trying to pick the best model, and then we're going to report the reliability from the model that is defensible, right? As it turns out, in this case, the reliability is highest for the congeneric model. So, all right, questions about the parallel model? Yes. I mean, you could if you wanted to, but it's still not tau equivalent. Like tau equivalent means you can constrain all of the loadings to be equal. So, I mean, if you wanted to mess around and say like, well, how much of the misfit is due to that item Y4? Like, because again, from an instrument development perspective, you know, if you're the one sort of designing the instrument, maybe knowing that Y4 is a dog might be a good thing to know, and that might cause you to say like, I'm going to get rid of Y4. That's a really bad item, and when I go through and I do some more work, I'm going to create some other items. So like you could do that, you know, but like it's if anything, if you have to unconstrain any of the loadings, it's not tau equivalent. Tau equivalent means all of them are constrained. So, you know, partially tau equivalent is still not tau equivalent. You know what I'm saying? But again, it may be useful to do that legwork, but it doesn't actually give you license to use Chromebox alpha or to say, you know, equivalent. It's like I'm almost pregnant or something. All right, other questions? Okay, so we're all good with measurement models and reliability. I mean, this is really useful too, because again, when if you stay in a latent variable modeling framework, which I would encourage you to do, you know, people are going to ask you when you're reporting your results, what are the reliabilities for these factors, right? And the right answer is not to go and just compute the Chromebox alpha, but to stay in the latent variable modeling framework, do this, and then you can report the reliabilities. You can report the you know, maximal reliability. You can report the you know, I would tend to report just the sort of the regular latent variable reliability that we were talking about. But you know, you can report either of those or both of those. So I think it's useful from that perspective. And again, if anybody ever asks you, like, how do you know, if you're ever asked to compute coefficient omega literally is the reliability computation that we talked about from the congeneric model. So you now know how to compute coefficient omega. Yes. I mean, if you're looking across time, so one of the things you want to be thinking about if you're looking across time is, do your items function the same way across time? So often when you're doing longitudinal measurement models, what you're doing is you're constraining the loading for the same item to be equal across time, right? Which is not the same as constraining all of the loadings within a time point to be equal. So like I would say most important for longitudinal modeling is that you're able to constrain the measurement weights to be equal across time, which is really saying, oh, this item is functioning the same way, as equally predicted by the latent variable, regardless of the time point, right? You know, if you can get to tau equivalence and you can get there across time, that's great. But if you think about it, then you're really saying the loadings of all of the items are equal within a time, you know, within a given time point and across time. So now Like imagine you have 3 time points with 4 items each. You're really saying those 12 loadings are all going to be equal to each other, which is, you know, if you can get there is awesome. But I would say like probably from a longitudinal perspective, most important, if you again, assuming you're doing this latent variable modeling, blah, 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 most important is being able to constrain the same item across time. Less important is being able to constrain across items. The same is true for multiple groups, right? Like most important is to be able, you know, you can still do stuff with congeneric models. You just, you know, shouldn't use Chromebox alpha, right? You just have to like know that that's the model and be sort of cognizant of it. But like more important is to be able to constrain your loadings to be equal across groups, even if the loadings differ across items within the same factor for multiple groups analysis. And for multiple groups, if you were looking at a tau equivalent in multiple groups, again, it's just for one factor, but for that factor, you would be saying you've got the same loading across all the items within a factor and across the 2 groups, right? Which is very, very stringent. And it is possible that one could be more like maybe really you've got tau equivalents in each group, but you can't constrain the groups to be equal. Or maybe you can constrain the loadings to be equal across groups, but you really can't constrain for tau equivalents, right? So those are like, you can sort of, you can look at these things sequentially. But yeah, good question. Other questions? All right, great. Ready for a new topic? Let's see where we get. All right, so now we're going to talk about nesting and equivalence. Current slide. Okay. So we really haven't talked much about equivalent models. I mean, I've made reference to this, and the rules for determining equivalence are awfully complicated. But let me start with some like sort of easier ones, and then we can sort of talk about complications. Okay, so when we talk about this idea of equivalent models, that means it's any set of models that, regardless of the data that you use, yield identical model. And so we're talking about the model implied variance covariance matrix here. Okay, so regardless of the data, you've got a set of models that yield identical model implied variance covariance, model implied variance covariance matrix. If you're doing models that include means and intercepts, then it would be actually model implied variance covariance matrix plus the same model implied mean vector. So when it says and other moment matrices, that's really what that means. So the moment matrices are like, you know, you've got variances and covariances, and then you've also got this mean vector. So, but again, sometimes we're considering means, sometimes we're not. But when we think about equivalent models, it's that all of these things are equivalent. And what that means, because remember that the fit is all about whether you're, you know, the comparison of the model implied variance covariance matrix, or when they're means, you know, too. But I'm just for simplicity going to say model implied variance covariance matrix, and know that in models that include means, that also we have to think about those means too. But fit is all about really how well does the model, you know, you take the model, right? You get these parameters, you use those parameters to get a model implied variance covariance matrix. How well does that model implied variance covariance matrix reproduce the variance covariance matrix, right? So that's really what model fit is all about. So if a given set of models gives us the same model implied variance covariance matrix, then that means that we're going to get the same residuals. We're going to get the same fitted moment matrices, okay? which means again, you know, model implied matrices and moments are going to be the same. We're going to get the same fit function, which means we're going to get the same chi-square value, which means we're going to get the same goodness of fit values because those are all based on those fit functions and chi-square and degrees of freedom, right? So any set of models that is actually giving us basically an identical model implied variance covariance matrix, those are going to be equivalent models. Now, again, simplistically, I mean, I've drawn sort of three really simple models here, but again, you can sort of imagine when you start to extrapolate from here. One of our problems is that, I mean, and these are silly, they're just identified models, right? But like A predicts B, B predicts A, or A and B are correlated with each other, which is what I have on the slide. Those are all equivalent models, right? And so, I mean, one of the sort of big challenges for us is that we like to sort of think that we know the direction of, again, I mean, I've always said, you know, be careful, these aren't causal models, right? You can't really infer causality just from non-experimental data with structural equation models, and that's all true, but frankly, once you know, if you draw a path in a given direction, you're implying, you know, even if you make all these caveats, it's not causal, you're certainly sort of telling the reader what kind of inference you want them to make about sort of the pathway, right? And the reality is that you can say A predicts B, and somebody from the lab at a competing university can say, no, B causes A, and somebody from a third lab can be like, no, there's probably some other variable out there that causes A and B, and they just happen to be correlated with each other, but neither of them cause the other. And the reality is that for all the fancy stuff we've done all semester long, there's nothing that we can use to like solve that problem, right? So, yeah. Yeah, well, yeah. Longitudinal data are better, for sure, but they don't necessarily completely solve our problem. Longitudinal data are way better than cross-sectional data, no doubt. And it is true that it really seems quite weird to draw a path backward in time, right? So you're certainly on firmer ground in terms of the direction in which you're going to draw your paths. But the reality is that just because, like, just imagine, let's say I collect self-concept in the fall and I collect kids' achievement in the spring, right? And then I have self-concept predict achievement, and it does. That doesn't necessarily mean that self-concept causes achievement, right? I mean, maybe I didn't measure achievement before, but maybe it was, even though I measured achievement after self-concept, maybe it was their prior achievement that made their self-concept higher, right? And so that's why kids with higher self-concept have higher achievement. Or maybe it's some other variable. Maybe it's cognitive ability that predicts both self-concept and achievement. And kids who have higher self-concept also tend to have higher achievement, but it's also because they have higher cognitive ability. So, you know, longitudinal models are good. They're certainly better, but they don't solve all of these problems. So, yeah, unfortunately. Anyway, but way better than cross-sectional models. Way better than cross-sectional models. Solve some, but not all of our problems. Okay. So anyway, here's the deal. So generally, the more saturated a model is, and saturated means the more parameterized. So a completely saturated model is a just identified model. A completely saturated structural model, that's the same thing as saying like a just identified structural model. And I'm really thinking here about structural models because, I mean, this is true, and this is true for measurement models too. But anyway, so. And all just identified models, if you think about it, all just identified models with the same set of variables are equivalent models. But think about how many different ways you can draw a just identified model, right? I could have all the paths going this way. I could have the paths going this way. I could have, there are lots of things you can do to create just identified models, even recursive just identified models. And those are all equivalent models. So it turns out the more parameterized the model is, the more equivalent models there are. So that's another good reason. That's like another thing in favor of parsimony, right? And another reason that we might want to trim paths that are not statistically significant, because the fewer paths we have, the fewer equivalent models there are. The models that are completely parameterized have scads of equivalent models. So anyway, so again, so our basic problem, but I mean, this is all meant to humble you, really. I mean, this isn't a lecture about why to trim models. This is more a lecture about, how to be humble even when you've got a cool model. So just because a model is consistent with your data, obviously, doesn't prove that that model is better than any other model. It might be better than all the other models you tested, but again, there could be hundreds of equivalent models lurking out there that you didn't test, because obviously you can't test the fit of two equivalent models because they have the same chi-square. So there's no way to actually say this equivalent model is better than this equivalent model, right? So if you have a good fitting structural model, it's fair that it suggests that, like, oh yeah, this is one plausible model that seems to be consistent with the data, and that's a good thing. But there's no way to say, like, oh, this is it. I found it. This is the model. Done. Solve the problem. All other researchers can go home now, right? Peace out. It's not, because a good fit for your model implies a good fit for all other equivalent models. I mean, I kind of hate this count, but it's good that I give it every year because it also keeps me grounded. So, like, here's just an example of 3 equivalent models. Now, these are not just identified models, right? There are all 1DF models, but they're all equivalent. So in the first one, you can see, and they all sort of suggest different things conceptually. You could sort of imagine if this were your data, right? The first model is saying, like, it's a total mediation model. So, like, X predicts Y and Y predicts Z. After controlling for Y, though, there's no direct path of X on Z. So Y completely mediates the effect of X on Z. Well, that sounds great, right? Second model says Y predicts both X and Z. And X and Z actually share nothing in common with each other after controlling for Y. But Y is kind of like the causal variable here, right? It's the sort of the leader here, and it's predicting both X and Z. And so anything X and Z have in common with each other is just simply because they share common variance with Y. And then the last one is just basically the opposite of the first one, which says, yes, no, Z predicts Y, which predicts X. So the Z X path is completely mediated by Y. And you can see how, like, those first and last one, you can see how those really are, like, equivalent. If you stop and think about it, like, of course, especially if they're cross-sectional, right? So again, after controlling for Y, there's nothing, there's no relationship between X and Z. So the story that you would tell in these 3 models is really, really different, but the model fit is going to be identical. And why are they equivalent models? Well, even though I sort of gave my story in a little bit of a different slant in all 3 cases, there was something common that I said it in different ways, but there was sort of a common theme that ran through, which was what? We all have made remember when we talked about over-identifying restrictions way back in the beginning of class? All 3 of these models have the same over-identifying restriction. We have 1 degree of freedom, so we have 1 over-identifying restriction. And that is that after controlling for Y, the correlation between X and Z is 0. We're really saying there's the partial, right? The partial correlation between X and Z is 0 after controlling for Y. right? So if you think about the model implied correlations, you know, oops, hold on, let's see. Right, so like here we've got, you know, A predicts B, right? Or sorry, X predicts Y predicts Z, and here's the A path and here's the B path, right? So what's the model predicted correlation between X and Z? It's AB, right? Exactly. And now, let's say we've got this. Z predicts X, Z predicts Y, predicts X. And again, what's the model predicted correlation between Z and X? BA, which is the same as AB, right? And here we go. In our third model, we've got Y predicts X and Y predicts Z. And what's the model predicted correlation between X and Z? AB, right? So like in all three of these cases, I guess I could have said what's the relationship between X and Y is A, right? What's the relationship between Y and Z is B? I thought that was kind of obvious. But so, you know, but also AB is the model predicted correlation between X and Z, right? So we're making this sort of same constraint in all three models. And the degree to which this model doesn't fit, right, is going to be sort of the degree to which I can't explain the correlation between X and Z with those two, the A path and the B path. All right. So really a way of thinking about that then is that in all three cases, what I'm really saying is that the correlation between X and Z minus the correlation between X and Y times the correlation between Y and Z is equal to 0. So, right, if you think about it, because I'm saying the correlation between X and Z is completely explained by the correlation between X and Y times the correlation between Y and Z. So really, I can sort of frame that as this difference, right? I can say the correlation between X and Z minus the correlation between X and Y times the correlation between Y and Z. That term is 0. That's our over-identifying restriction. And the degree to which, you know, and if that's not true, that's going to cause some misfit in our model. Okay. So again, you know, this is the same thing that I was just saying. These are the same basic three models, right? That we have that same restriction. We have a 1DF model. We have the same restriction across these three models that predict that partial correlation between X and Z after controlling for Y is 0. Same fit, different conclusion. Okay, moving along. All right, so here's an example. Of course, like when it's three variables, right, it's sort of easy to kind of come up with a small set of models that are equivalent. But like, what about this one? Here we've got a just identified model. Like, how many other just identified models are, how many other ways could I draw this just identified model? Like a lot, right? You know, here are two more examples that look really different from the first one that are equivalent. So look here, this first one is saying like A and B predict C and D, predict E and F, right? The second one is like, you know, A and B predicts C, which predicts D, right? Here I've got E's predicting F. You know, over here I've got E and F sort of predicting C and D, right? I mean, and again, it's not even just a simple reversal, but these are just two examples of equivalent models for that model. So there are like a boatload of equivalent models. And again, especially with just identified models, there are so many. I mean, again, there are lots of equivalent models even for non-just identified models, but the more parameterized the model, the more equivalent models there are. So Hirschberger came up with these replacing rules that will help you to sort of determine whether two models are equivalent. And so, okay, you can sort of, again, this is helpful when you have like a big model, big structural model. So the focal block is like the block that we're sort of, the block that includes the sort of relations that we're altering to produce an equivalent model. Okay, so like imagine in this example here, let's say I'm going to mess with the parameters maybe in here to produce an equivalent model. Again, you can mess with lots of different parameters, but just to sort of take things one at a time, because this gets really messy. So we have this focal block that includes the relations we're trying to alter to produce an equivalent model. The preceding block is going to be a block that sort of precedes the focal block, and the succeeding block is the block that comes after the focal block, okay? And replacing rules require what's called limited block recursiveness. So the model doesn't have to be completely recursive. It could be somewhat non-recursive, but it needs to be block recursive. We're going to talk a lot more about non-recursive models next week. But here's how it works. And again, this is not easy, I know, but like imagine you've got two variables in the focal block, okay? And they both receive paths from the variables in the preceding block, and they may send paths to other variables in the succeeding block. And let's say that VI is predicting VJ, okay? So, all right. I can take that direct path from VI to VJ, and I can replace it with a residual covariance if the predictors in VJ are the same as those or include those of VI. So basically, the path can be replaced by a disturbance covariance when the predictors of the effect variable are the same as or include more variables than the predictors of the source variable. I know there's a lot to remember. You don't have to remember all of this off the top of your head. I don't remember all this off the top of my head. I go back to Hirschberger. And then, so then there's also like within you can see this, these are the simplified rules. You should see the full gamut. So within a block of variables, at the beginning of a model that's just identified, direct effects, correlated disturbances, equality constrained reciprocal effects are all interchangeable. So, and if the two variables are exogenous, you can substitute in a covariance. So basically, that means that if you have y1 predicts y2, you can replace that with y2 predicts y1. The disturbance of y2 and y1 are correlated, or an equality constrained reciprocal effect, which again, we're going to talk more about next week, but that actually means that y1 predicts y2 and y2 predicts y1, but we make an equality constraint on that reciprocal causation. And at subsequent places, again, you can do all of those substitutions. So when you start to follow that logic, again, here's just a simpler example. Here's the original model, and here are three equivalent models that look really, really different. And you can see what I'm saying here, like, here you've got between neurological dysfunction, you've got a path going okay, you've got a reciprocal causation path here, right? Anyway, these are all equivalent models. So, again, here are three. I mean, we can think about this for measurement models too. These are three equivalent measurement models. Again, at the outset, they don't necessarily look equivalent, but if you stop and think about the covariance, that sort of the restrictions that are being imposed on the variance covariance matrix, all three of these models are actually imposing the same restriction on the model implied variance covariance matrix, which is that the covariance between x1 and x3 times the covariance of x2 and x4 minus the covariance of x1 and x4 times the covariance of x2 and x3 is equal to 0. So basically, it's saying that the covariance of 1 and 3 times the covariance of 4 minus the covariance of 4 3. See the pattern there? That in this model, the restriction is that difference equals 0, which means that those sort of the one set of the one product set is equal to the other product set. Sat down and you drafted this out and did some covariance algebra or just did the tracing rule. you would discover that that is the restriction. But at first blush, it isn't totally obvious that those three models are equivalent, right? I mean, then that's the problem. Okay, so again, so Hirschberger for CFA, he has a what's called a reverse indicator rule, which means you can respecify any one of the observed variables in a CFA. This one is really concerning if you stop to think about it. You can respecify any observed variable as a cause indicator, while the rest remain as effect indicators. What that means is got four variables. That's my simple CFA. I can take any one of these four variables and make it a predictor of the factor. I can say E1 predicts to the 4. These two models are equivalent. Holy crap. So wait a minute. So V1 is either the cause of the factor or it's one of the indicators of the factor. Right? That should give you pause. So again, this is an example. Like here's an original. You could have. I mean, when you stop and think about this, it just starts to make you really question everything in the world. So like imagine here, like phonics, word recognition, letter recognition, and word fact skills, all reading skills. Right? And I think I'm measuring a reading latent variable, a variable. And then the person from the next lab comes over and is like, no way, phonics. Phonics is the predictor. Reading is measured by word recognition, letter recognition, and word attack. But it's really your phonics skill that predicts how well you do in reading. These two models will have the same chi-square. They have the same degree. Model. No way that you and your rival are going to be able to settle the score. This is 12:15. You know what this means? You lucked out. You don't have to do the Kepler question on the homework because it didn't show you how to do that yet. So just do the reliability part of the homework. Don't worry, I will repost it without the Kepler stuff, but just worry about the reliability part. And next time I can show you quickly how to do the Kepler stuff, which is not that hard, but we're out of time. All right. Yes. Oh, it shows up at 12:30? Okay. Shows up at 12:30. 15 minutes. Sorry. So you had questions for me, right? You want to do it now? Friends, you want a handout? I need to make handouts today. All right. What's up? Okay.
Right.
Okay. So model girls, let's see. Which model is this though?
Actually, CMV. Well,
Yeah, so you
we
do the
don't have-
constraint condition, the constraint just identified model. Then you do the constrained unconstrained conceptual model. Then you do the constrained conceptual model in E,
Yes.
right? Okay. And then so
And then we constrain the
you constrain all the structural paths to be
yeah.
equal across the groups, right?
Yeah.
Yeah. So that looks. Wait a minute, let me see. Which one is this though? This is not,
This is this one.
I was gonna say, because this looks like, yeah, this looks like variances are constrained to be equal. Okay, good. So, yeah, because here you've got the paths constrained to be equal, right? Here you've got the exogenous and disturbance variances constrained to be equal. That looks good. Okay.
And then I put them into separate lines.
Well, as long as you've different, I mean, I think this is good. Like,
Okay.
you need different numbers to make sure they're not constrained to be equal. I like to put stuff on different lines. It makes it easier when you want to get, like, eliminate constraints and stuff. Then you can just use the little, you know, the little exclamation point. So I find it easier to just write stuff on a lot of lines, and then I can message it more easily. But yeah, so this looks fine. So yeah, so you're constraining the exogenous variances and the disturbance variances to be equal across the two groups.
And then
Okay.
I have to constrain.
Covariances. So the covariances in this model, what have we got? We've got a, so it's math with reading,
Okay, and
but it's also those, right? And so you're just going to do the same thing. You're going to put
Yeah.
just, you know, you can use new numbers, right?
Yeah.
Don't use, go to 10 or not 11, you got to go to 12 or whatever. But yeah, so you're going to constrain this with this to a number that is also constrained across the two groups, right? This with this constrained across the two groups. This with this is constrained across the two groups. And then, yeah, and then the endogenous covariance between math and reading is constrained
Okay.
across the two groups, right? Yeah. So, I mean, it looks like you're doing, to me, this looks like you're doing everything right.
and then we have to compare them.
Yeah. And so what I'm asking you in this whole like march from A to H is you're literally just making a set of increasing constraints. I'm not asking you like to do any partial, right? Like you're going to see that at some point the fit is going to get way worse, and that's okay. And I just want you to kind of continue on. And then in the next question, it asks you, what would you do, right?
Yeah.
Like, and based on what you have in question one, you should have a really good hunch then about like where things started to go south, right? Something that you could do. Does that make sense?
Yeah, but how?
The constrained, oh, wait a minute. So hold on. The constrained, just the unconstrained conceptual model shouldn't be the same as the constrained conceptual model, right? Is it?
Yeah.
Oh, well, okay. They're the same?
Yeah.
Okay, well then in that case, yeah, so that's right. Then they are the same in this case. Well, no, you can't compare them if they're the same. Then they're the same. Yeah, exactly. Okay, so can we constrain the conceptually omitted paths to be equal? Unconstrained, yeah. Model from C, deleting the paths that were constrained to be equal if they're not statistically significant, right? And the unconstrained, and then the constrained. Let me just see here. C and D. Go back. C. Scroll it back down. So C, no, this way. I just want to see. Yeah, okay, yes, that's right. So C and D should be the same, but then E is the one where you're constraining the conceptual paths. Yes. That's right. That's exactly right. Sure. Mhm. Okay.
So I compare the intercept, so compare understand is different.
Mhm. Yeah, we didn't constrain it, right? We allow it to vary. Yeah.
Sorry, we allow it to vary.
Uh-huh.
Now, but did the parent interpretation correctly? In girls, is equally explaining the variance of girls and boys was they're basically very similar. Is that the
Well, it's the variant, so it's the variance in IQ for girl. Like
Yeah,
if
the variance of
the
IQ.
variance for IQ is an IQ here is actually an exogenous variable,
Mhm.
right? So it's just that the variance in that variable is the same or similar, right? Is basically the same across the two groups. You said something at the beginning of that wasn't right. I forget exactly what you said, but something, but
Yeah, the
it's,
model
it has nothing to do with explaining because it's an exogenous variance. The question is, if it's an exogenous variance, the question is like, is the variance the same for boys and girls? Like, is the variance in IQ the same for boys and girls? Like, let's say it's not. Let's say the variance in IQ is bigger for boys than girls. What would that mean? That would mean, let's just say boys and girls, and actually, I have a good example of this from the ECLSK where in kindergarten, boys and girls have the exact same mean on math, but the variance was higher for boys than girls. And what that means is that, like, yeah, okay, boys and girls, their average math skills are similar. But if you look across the continuum, like if you just went to like, you said, I'm going to look at just like the bottom 5% of kids who are the most at risk, it's going to be mostly boys because their variance is bigger. And if you go to the top 5% and say, who are the really mathematically talented kids, it's going to be mostly boys because their variance is bigger. So even though like the mean for boys and girls was spot on equal, because the variance was different, like the distributions, you know, you can sort of imagine what that looks like, right? Like something like this. I'm going to draw it like really vague. Like that's not what it looks like. Way more dramatic than it was. But what that means is that, like, you know, but their girls tend not to be as extremely low or as extremely high. They tend to cluster around the middle much more than boys do. So, I mean, so that is interesting, right? It is interesting if you find that the variance is different, but it has nothing to do with like, you're not like you're not explaining the variance of boys or girls because this is not variance. You're just saying, are those variances?
A lot, thank you.
Sure. Other questions?
Yeah. Well, you can answer it for the last question because they were looking at which model to improve, but you did mention that when you're looking at the model to improve, you look at 1E.
Well, I mean, yeah, probably.
Probably.
I mean, that would be a good place to start. I mean, right, what I'm asking you to do in the first part is just make a series of increasing constraints.
Yes.
You're going to get to a point where things fall apart, right?
1E.
Yeah. I mean, I'm not saying that, but if you say that, I'm not saying it. Anyway, but the point is when things fall apart, right? When you make these, so like in that second question, so I just want you to keep making constraints. I don't want you to like free anything then. But then in that next question, it's like, okay, based on what you saw when you made these increasing constraints, can you suggest something that you think should be allowed to vary freely?
Okay.
That might improve the fit of the model. So now I'm asking you to like, yes, and if you think it's like, yeah, it should be kind of obvious based on your march through the models as you make those increasing constraints where there might be a problem, right?
Yeah, that's
Okay.
because it's just the biggest one in the
Okay.
Just guessing or something else.
You should do whatever you think is going to make the model the best. I mean, you're not going to get points for originality. You're going to get points for improving the model fit, right? So, you know, well, model fit and theory. Yeah. But like, you know, I wouldn't try, like, there are all kinds of constraints you could make that might not improve the model fit at all.
Yeah, exactly. That's what I'm. The obvious one is this one, but like,
Yeah.
I want to do that one.
Well, why don't you want to do that one? It's obviously the problem.
Do that one.
Yeah, but it's the problem, right? Like it's like begging to be freed. It's like, please, Claudia, let me be free.
So the question is like,
If you ignore it, that's mean. You're like torturing that path. Like you've got it like constrained, and you're not letting it go. You should just do one at a time. And you should start with the most obvious. I appreciate that you want to do something different. But there's lots of room for creativity in SEM, but I don't know that this is the place to do it.
Okay, thank you.
No. Go with the obvious. I think that's a good choice. You're welcome. And you know, modification indices are one place, but another place you could look, right, is look at the model where you don't have the paths constrained, right? The conceptual paths constrained, and you can kind of eyeball, and you can see like, that's obviously not a statistical test, but your eyes, the ocular test is a great place to start. If you're looking at them and you're like, wow, the path for boys is really different from the path for girls for this parameter, that's a good place to say maybe that's the one I should free, even without the modification indices. But my guess would be that the two would reinforce each other in terms of decision. Yeah. Yeah. You're welcome. Oh, I think I forgot to stop recording. Oh my. Okay, I'll stop now. No, I have to like 1:45. I'm good, but let me stop recording. Please.